Improper integrals are integrals of type where the interval of integration is unbounded. So it could be unbounded at one end or both ends. We are going to consider a couple of examples of improper integrals of type 1. The first one is where the upper limit is infinite, and the second one is where both limits are infinite. One is negative infinity, the other is positive infinity. As our first example of improper integral of type 1, we consider this improper integral of 1 over x to the 1 over p over the interval 1 to infinity. Now, by definition, this is equal to limit of the integral 1 to a dx over x to the 1/5 as a approaches infinity. Now let us find out first the antiderivative of 1 over x to the 1 over 5. And so let's integral. This is the same as x to the negative 1 over 5 dx, and by the exponent rule, this is x to the negative 1 over 5 plus 1 divided by negative 1 over 5 plus 1, which is equal to 5 over 4 times x to the 4/5. Therefore, limit a to a approaching infinity of 1 over a dx over x to the 1/5 is limit a approaching infinity of 5 over 4 a to the 4/5 minus 5 over 4 times 1 to the 4/5, which does not exist because as a approaches infinity, this thing approaches infinity, and therefore this integral is divergent. Okay. Now for our second example, we note that we observe that both limits are infinite. So negative infinity to infinity dx over x squared plus 1. Since 1 over x squared plus 1 is continuous everywhere in the open interval negative infinity to infinity, we can select any point between negative infinity to infinity to split this integral. So why not choose x equal to 0? So therefore I can write this as negative infinity to 0 dx over x squared plus 1 plus 0 to infinity dx over x squared plus 1. To evaluate each of these integrals, we will have to apply a suitable limit to the suitable integral dx over x squared plus 1. So let us first of all find out antiderivative of 1 over x squared plus 1. Now we know that dx over x squared plus 1 is tangent inverse x. So we find now the integral negative infinity to 0 dx over x squared plus 1 is limit a to 0 dx over x squared plus 1 as a approaches negative infinity, which is limit a approaching negative infinity of, because the antiderivative of this is dx over x squared plus 1 is tangent inverse x, so plugging in the limits becomes tangent 0 minus tangent inverse 0 minus tangent inverse a. This is 0, and as a approaches negative infinity, this is going to approach negative pi over 2, and therefore this becomes negative of negative pi over 2, which is equal to pi over 2. We will now work on the second one similarly. 0 to infinity dx over x squared plus 1 is limit b approaching infinity tangent inverse b minus tangent inverse 0. Once we notice that this can be written as limit of 0 to b dx over x squared plus 1 as b approaches infinity. Now this part is 0, and as b approaches infinity, this will approach pi over 2. Therefore, this is equal to pi over 2 minus 0, which is pi over 2. Hence, going back to the original integral, which is negative infinity to infinity dx over x squared plus 1, which we wrote as negative infinity to 0 dx over x squared plus 1 plus 0 to infinity dx over x squared plus 1 is equal to pi over 2 plus pi over 2 equals pi. And once again we find that this integral over here is convergent. we hope that these examples illustrate how to discuss the convergence or divergence of improper integrals of type 1.